All right, producer, you think we're ready to begin? All right. Let's rock and roll. Okay. Yeah, man. All right. So, oh, my button didn't work already. That's awesome. All right. So this is titled the Artificial Intelligence Workshop. This is going to be about a subset of artificial intelligence called neural networks. When you hear about artificial intelligence in the news, or just in general on Twitter and whatever, it's almost certainly referring to some type of neural network, as this is arguably the most advanced form of artificial intelligence that exists right now. But you know, an artificial intelligence is something that exhibits intelligent patterns. So that could be any type of algorithm that makes decisions based on like the circumstances that you're in. And we're going to learn about what I think is the coolest version of that. So what is a neural network? Who here has heard the term neural network? Okay. Who here knows what a neural network is? Perfect. Who you know, we probably have heard that like this is an algorithmic structure meant to mimic the brain, which is a pretty exciting concept. Let's talk about, to begin, oh, this is gonna make me go through all these things. Okay, let's talk about neural networks that are out in the wild, things that we might be familiar with, just to get a little basis here. Actually going on, like literally in a few minutes, is going to be Tesla's AI Day, where they're probably going to be talking about strides that they've made in Tesla Autopilot. So neural networks are things that neural networks find themselves being particularly useful for tasks such as automated driving. Similar to Tesla Autopilot is OpenPilot, which this is a GIF of right here. You may have also heard recently about image generation neural networks such as DALL-E and Stable Diffusion. In the past few years, things like deepfakes, things that can sort of transfuse somebody's face onto another person's body. Basically, all advanced forms of natural language processing. You know, like Google Assistant in my phone is wicked fast at figuring out what I'm saying in my voice to text. That is a neural network. When people refer to the algorithm, probably referring to a recommendation algorithm, yet again. And I think especially after like convolutional neural networks and after you know, like consumer graphics cards got a lot of memory bandwidth and they got a lot of flops. A lot of new businesses started to pop up around neural networks. I interned at a company called ChemImage over the summer that convolutional neural networks as of like 2015 completely changed the way that this company operated, even though they've been around for over 25 years, because the data that they deal with has very, very subtle patterns inside of it. They basically do spectral imaging, where you can take images of a thing and filter out different wavelengths of light. Different elements absorb different wavelengths of light. So if you know, like if you have like an index of like what wavelength a particular element absorbs, you can figure out what elements are inside of a thing without like X-ray or without anything like that. This is how astronomers figure out what's inside of like atmospheres of faraway planets, is seeing what wavelengths of light are absorbed through the atmosphere when it comes through. But like parsing that data is very difficult and basically impossible for humans. The patterns inside of it are non-human understandable. And that's going to be a very big concept today, is that like the abstractions that neural networks can find are things that we would have almost it would be an impossible task for us to articulate. And if we can't articulate it, we can't necessarily write that algorithm ourselves, like in say, you know, in Python or something like that. So let's talk about like literally what are neural networks. I don't know how many thingies there are here. I just want to see all of them. All right, that looks like all of them. Let's go into, I'm gonna have to say this at the beginning. I'm gonna try to get through this pretty fast, but there's going to be a lot of math that we're going to, not a lot, a little bit of math that we're gonna have to cover. Similar to like cryptography, the driving force behind neural networks is an algorithm called backpropagation. And I honestly don't see how somebody can understand what backpropagation is without understanding just a little bit of the calculus. If you've taken Calculus 1, you basically have all the prerequisites necessary to understand what we're going to go over. But let's first define our goal when what we're trying to come up with here. We're trying to come up with a function that can tune itself. So let's start off with a very, very simple function. This is just a third-degree polynomial with one variable that we can change. And look at how dramatically the function changes. If we have some way to interpret what that output means, and we have an intelligent way to pick that variable, we can tune this function to do some sort of arbitrary task. This might be like based on the torque that you're experiencing, how much voltage you might want to apply or something to your motor. This, but there's not that much fidelity in a function like this with only 3 variables. But ultimately, at the end of the day, this is a function that takes an input and an output, and there's a bunch of stuff happening inside that transforms that input into the output in some sort of vaguely in some sort of consistent way. So how can we generalize this concept such that we can have a lot higher fidelity control over the way that we can change that function? So before, in this example, we only have one value that we could change. I guess we could change the other coefficients. So we would have 4 values that we can change, but ultimately that's not that much control over this function. So what sort of structure can we come up with that gives us a ton of control over this function? I'm basically just going to jump right into what a neural network is. What we have right here is this structure that I'm describing. So what's going to be different about this function versus the previous function is that data is going to propagate through it. Ultimately, it's still like processing it in some type sort of like solid state sort of way, but information propagates through it. So we can first of all figure out that there are like abstractions at various like degrees of propagation. Let's see what's on the next slide. Just I think there's going to be more words. Perfect. Our inputs are not just one. Before we had one input. Now in this example, we have we have 3 inputs. So this network can only ever take in 3 inputs. It can only ever output 2 things. But look at the number of where I'm going to say the values that we can control. I'm going to call weights from here on out. This structure, instead of just 4, this structure has 36 different values that we can use to decide how this function operates. Those values are the connections between these nodes here. So every node in a sequential layer like connects to the next one. So to figure out how many different like values we can adjust, we would do 3 times 4 plus 4 times 4 plus 4 times 2 is 36, I'm pretty sure, which is like a pretty cool, interesting structure. Let's see if there's anything else here I want to talk about. I don't think so. I think we're going to come back to this in the future. No, this is literally, okay. So it turns out that this structure that I have just described is something called a universal function approximator, which is an absolutely wild concept. So given enough of these parameters, like given enough weights, and given like the perfect values on those weights, this structure can approximate any function. So think of anything that you can turn into a function where it takes an input and delivers an output. Like, are we talking like all of computer science? I mean, this is not a program, but there's a slight way that you can restructure this such that it can approximate any program in general, if you know how you want the program to operate, and you can say whether it operated right or wrong. So obviously the big question then is like, how do we get the right values of those weights? Like I said, given the right values of the weights, you can approximate any type of function. That might be a function that might be like sine x, or that might be a function that like takes in an image and points out where the dogs and cats are, or it might be a function that takes in an image and just like makes it blue, or you know, what other functions might we use? A sorting algorithm or something like that. Any function that you might use in your program. But how do we actually get what those weights are? And that's like the crux of that's going to be the crux of this mathematical problem, and why we need calculus to understand how a neural network works. Hello.
Spencer, sorry. We have a question from the Zoom chat that says, is this stochastic gradient descent to get the weights?
Is that a question? Well, yeah, stochastic gradient descent is a, we will definitely, the answer is no, not exactly. But yes, in some ways. That is a particular way that you can go about adjusting the weights, or figuring out what values you want to have on those weights. So when I say like how many weights do we need, one structure say we want to write an algorithm to identify a handwritten digit as like an actual number. I mentioned earlier that there are concepts that neural networks can discover that are non-human describable. And that's kind of like a declaration that I'm making that it's non-human describable. But I don't know how I would come up with the descriptions such that I could write an algorithm that's able to figure out that like this weird 9 is a 9 and this like blob is an 8. And you know, these various different types of 4s are 4s and so on like that. That would be a wicked hard program to write, to like parse those pixels and figure out where curves and lines and edges are, and then what the necessary like actual high level descriptions of these numbers look like. And it turns out that if you want to make a neural network to do this, you can do it with about 26,000 weights, which is an absolute whack ton of numbers. And you know, the way that we get that is that like we're gonna say this is like a 28 by 28 image. 28 squared is 784. So we need 784 input values to represent the pixels in that image. We're going to pass that to a layer with 32 neurons in it, and then a layer with 16, and then output 10 because there's 10 different numbers. And if you like were to figure out how many weights there would be in there, it would be some number around 26,000. I didn't write the full thing. And that's something that we're going to do today. Is we're going to write an algorithm to classify these digits. This is a very famous classic data set in machine learning called the Mnist Data Set, published somewhere over 20 years ago. But this is a data set that you could just download that's like really well compressed, small, and it has like 60,000 instances of numbers. So it's usually like, if you're going to write an algorithm, that'd be a little baseline test to make sure that it's kind of working right before you move on to like your more specialized data. There's also a lot of studies related to this, so you should be like, I should be able to get like 0.5% accuracy or 0.5% error with this particular structure, and I'm not. So what's wrong with it? So these are just some more images of kind of what this type of structure looks like, just to get some more visualization going. I should probably talk about what sort of math is actually occurring, like when these like point to these other neurons. Does anybody here like know how to do a dot product or know how to do a weighted sum? Those are the same thing. Pretty much the value that like I actually have an image of it way back here. Just so I don't have to write it. Yeah, here we go. Oh, it's covered up by the thing. So the way that this is defined is like that we can just multiply the output of like this previous neuron with the weight connecting it to the output neuron and add it to like all the other ones. And we're going to get some sort of value here. Don't mind this activation function for now. That's just a way to sort of help the algorithm later on in ways that we'll come to understand. Does anybody have any questions?
So is the math required just dot products? Or I heard there's a lot of other like matrix multiplication.
Linear algebra is used in machine learning, but primarily, I think that the biggest piece of math to understand what's going on is calculus. But like linear algebra is used to make neural networks wicked efficient. If anybody here is familiar with like what a tensor is just like an n-dimensional array. So instead of a value, you might have an array of values. What if you had an array of arrays, and then an array of arrays? The computer science used to process those types of objects are thousands, if not tens of thousands or hundreds of thousands of times faster than like dealing with individual values. Because inside of computers store values in arrays, not as individual values. So you can move around arrays like giant blocks inside of like memory and through the CPU and stuff like that. Yes?
So we have a question. Chase asked, I assume that we need knowledge of vector calculus?
If you're, I do not think, no, not for this presentation, no. If you're going to go like read source code, then perhaps. What you actually want to search for is tensor calculus. There's like a Wikipedia page about it, and it will tell you how the calculus that you learned in your class applies to like these, objects that have just like an arbitrary depth, an arbitrary number of numbers between them. Yes.
Second question from Andres. ReLU or sigmoid for activation function?
ReLU on hidden layers, sigmoid on the output layer is my opinion on it. Ultimately, you know what we need though, Andreas? We need meta networks that are capable of deciding these hyperparameters for us. We should not be deciding these things. If there's anything that's to be learned from neural networks, is that you should be defining as few things as a human as you can. The most successful car autopilot algorithms right now are the ones that have defined the fewest things about the world to the network. So they did not tell it, go find me a crosswalk, go find me a person, look out for stoplights. All they need to show it is how people drive, and it will figure out those abstractions on its own. Because as soon as you start to tell it things about the world, you're going to miss things. So there's like a famous story where Uber used to have a self-driving car project that has since been canceled. But there's like this funny story where Uber had a particular like segmentation model in their thing that would say like, look out for bikes because you need to track where the bikes are in the scene such that you don't like run into them. And the car is driving around in the winter, so there's snow everywhere, and it drives by the like the bike lock thing. There's like two bikes in there, and it just like tracks the bikes. It's like, okay, it makes the loop, it goes around fine. The summer comes around and all the snow melts. Car's driving, it hits that same area, it comes to that intersection or whatever, system totally crashes. Like, what happened? They look into it, and it turns out that the network is like trying to simultaneously track every single individual bike in this massive rack of bikes. It's like trying to track 40 different things in a scene that are all irrelevant to us. Like when I see a bunch of bikes, see that's a bunch of bikes. And that's an abstract. What are you gonna do? Are you gonna put an exception in your code that says if you see a bunch of bikes, call it a bunch of bikes. If you see two bikes, call it two bikes. It's like, these are descriptions that we do not want to add because, what if it's not a bike? What if it's a scooter? What if it's no? So defining that tangent is about defining as few things as we can ourselves anyway. Once again, non-human understandable. Come on. All right, so let's get into tuning the parameters. I don't think that this is actually. Ultimately, the value that we are chasing is how much did each weight. So we have like we might have 28,000 weights. We might have millions of weights inside of our function. Or in this case, we might have 3 different values that that we can change that affect the value of the output of the function. So how are we going to figure out how much we ought to like alter these values? if we don't know how much they affect the output. That's the important thing to us. And does it sound like a familiar concept to anybody? If we like wiggle this value a little bit, how much does it wiggle that value? So we're gonna do a derivative. Yeah, well, technically called gradients. If you take calculus 3, they'll call it a gradient. Gradient's just derivative, multiple. It's stupid. With multiple variables. So over here, I've calculated just what our derivatives would be if we like set up these if we initialize some random values as our parameters. What you're going to do when you start a neural network, when you first initialize one, you're going to put random values, and it's your job to figure out what those values ought to be. So let's say we initialize these at random. These derivatives, if we take the derivative of the output, which is f of x, with respect to a affected the output by some multiple of 4.84, which means that A had a very large effect on the output given the input. B had a very small effect on the output, and C has a perfectly linear relationship, or just like this one-to-one correlation. Well, I don't know if I really want to say that relationship with the output. However, once you change C, we'll change the output by that much exactly. Yes.
So that's in relation to the degree of the term.
Well, in a way, yes. But I didn't go over how to take derivatives in this instance. But in the case of A, the value that we want. Did I do this right? Or did I have other values up here?
2x and then
Oh, I think these are, wait, what did I do here? Oh, I think I had, yeah, no, that should be 24, right? Yeah, anyway, those must have been old values. I think I switched them around. My fault. That's not a big deal. We'll get to more later. Yes.
The derivative term, it says like df dA.
We're taking the derivative. A is a variable. So A is a constant when we make it a constant, but technically A is variable because we can change A as we please. So we're going to take the derivative of f with respect to A. You can treat. Oh wait, no, I totally. Wait a minute. I didn't tell you what the x is. I did do it right.
Oh.
I think. Hold on. We'll get to it. I think I have more of these. Yes. So this is like a better example. Actually, let me cover this first. So we don't actually just want to take the derivative of the output with respect to these variables. We actually want to take the derivative of like how wrong we were or how right we were. So we need to know what we wanted the function to be. So in this ahead example, let's say we put in a value of 3. So we're going to let our x be 3. We're going to do f of 3, but we hoped to get a value of 12. If we use that function L on the left there, I'm going to, from here on, refer to that as the loss, which is the value that which is a function to represent like what your error was. So how right were we? If we put if we put 12 and 10.25 in that function, we should get 1.56. Additionally, the other observation you might want to make is that if both of those values, if the function is correct in that f of x equals the value that we wanted, the loss is going to be 0. Because there's not going to be any change that we want to make. It was perfect. So that's kind of the big observation that one might want to make. But so we can. This is pretty much the same process as before. We're going to take the derivative with respect to these various different variables there, A, B, C, and D. And the way that you do that, I actually did these kind of I did these somewhat in reverse, but you'll see why this order makes sense in the future. So you can take the derivative of L, so dl, dd to get D. And that's going to just be, I guess I typed it wrong, but negative 1.76, right? Yeah. DLDC is going to be, since C is just multiplied by a constant, it's going to be that value AX plus B, which is this, so we get negative 17. And like what you need to understand about what that value means is that if we increase the value of C, our output, let me think about this really carefully here. Hold on. If we want to get our value closer to what we hoped it to be, we want to subtract negative 17. So we're actually going to add 17. So that value C is having actually a very negative effect on the output, and it's having a very dramatic negative effect on the output. So if we're going to pick one value to change, it's probably going to be C, because it has by far the biggest derivative of all of them. Anyway, yeah. So down here, I calculated what the gradients of all of these values are going to be, and then we don't actually want to change them by exactly what the gradient is. We probably want to change it by a much smaller number. Otherwise, we'll end up like totally overshooting. This number right here, 0.01, is often called the learning rate. So at first, you want to change it a lot, and then a little bit later in your algorithm or in your training, you probably want to change it by a little bit. So the learning rate you'll often notice goes from like say 0.1 to 0.01 and so on. But if we change it by 0.01, which is just a random value that I pick, we actually get really close to what we wanted the value to be, which is 12. So as you can see, by taking the derivative, we're narrowing in on the value that we wanted. So the big kind of meme that is used, how are we going to actually like put this into code, like these derivative rules? Because you probably know the derivative rules like off the top of your head, but like writing an algorithm to do that sounds horrible. Luckily, there's this nifty little theorem called the chain rule, which says that if we like describe everything as like a function composition like this, so if we think of like a multiplication as a function that takes 2 arguments, and we think of like the addition as another function that takes 2 arguments, we can think of that as a function composition. So here I've described the multiplication as G and the addition as H. And you can actually like take the derivative, again, I keep saying that. How many things are there here? Here we go. The chain rule basically says that we can do this little thing on the bottom. We can do these various things. So we can take the derivative of the inside thing, and we can take the derivative of the outside function, and then leave the inside the same, and then multiply that by the derivative of the inside thing. We can do that over and over and over again, and it turns out we can find the derivatives of these little variables in the middle. The other observation to be made, which is really cool, is that we keep calculating the same things. So we don't actually have to get all of these. We already got, let's see, we already got like, which one did we get? Yeah, okay. We've already calculated up to DJ, DH. So we don't have to redo this calculation. We could just like steal this value from over here and grab a few more. And this is if you've ever heard of the term backpropagation, that's what that's what that's referring to, is that we're actually going to like do the outermost one first and then step back and back and back and back using this chain rule. Yeah, this is pretty much what I just said. Okay. To emphasize this, we're just going to switch over to doing some code.
You said that was a theorem?
Well, the chain rule is a rule, a theorem, basically a little
Okay.
chain rule.
Yeah, but never mind.
So like, how you would like
What was that?
so
how would we code the chain rule?
Yeah. Is it like a recursive function?
It is a recursive function. So I have some code here that we can look at to see how that's going to work. How can I like get rid of this thing? This is annoying.
I mean, you can do it. If you grab the green bar.
Grab the green bar.
Yeah.
Like,
Yeah, if you grab it on the green bar, like it's the green bar with the red stuff, just grab it. And you can
well, there's a way to make it go into the like minimize itself, but whatever. Hmm?
maybe just put it, maybe just put it at the bottom. That's like that's where main video loading
Mini
meaning.
controls, yeah, there it is.
That?
I'm putting mini
Next to
controls.
share computer sound on top.
One
Yeah,
more.
so go down. One more.
One more.
Yeah.
Perfect. So I was hoping to like code this, but it turns out it's a little bit more to code than I wanted to do, or we just wouldn't be able to make like very good time through it. So now we've made it through all that through all that math stuff. Let's think about how we might actually go about coding up the chain rule. So this is a little project. It's not necessarily practical for making like large scale neural networks, but I think is really useful for learning how they work. This is Micrograd by Andrej Karpathy, who is the former head of AI at Tesla. And there's really only two things, or primarily there's one thing that we have to worry about, which is, or that we just have to know about, which is this value class, which really all it is. Let's go into like a test environment and I think I already have some stuff. Let's see what we got. We'll start a new one. Oops, it's back. All right, from what was it? My import value. I don't even remember what it was. I think it's. So let's see if this works. So all this is really like a wrapper for value. We need to store additional information about like numbers. So if we have a value, Python cannot normally like store like what values created that value. If we want to take the derivative of some sort of output with respect to something that created it, we need to store all the things that like created that value inside of that value, which is really all this little value class does. So if we make a value 3, or let's say A equals value 3, B equals value of 2. All this is like the number 2 and the number 3. Oops. And then we can calculate C, which might be A times B. And then what if we want to do, let's do a C dot backward. What would the derivative of C be with respect to A? It's going to be, anybody want to say? It's going to be B. It's going to be 2. So if we were to print A dot grad, so how much did A affect the output of C here? We got to do this. Nope. This is a very inconvenient like angle to type at. Oh, cool, we got 2. So that's kind of the big idea behind this. So how does that actually work? How do we actually like store those types of things? I won't spend too much longer on it. First of all, we're going to store just the data of that value. So what value is it? In the case of 2, it's the data value is just 2. Additionally, we're going to want to store all the children of that value. So what are all the values that made that value? So in the case of like that other, if we go to the thing that we had before, oops, yeah. The things that made C were A and B. So those are going to be the children of that value. And then we're going to define some operations, because this value object is not actually a real number, like in Python it might be. So we have to redefine what add looks like. And guess what? It's just add. But what we also want to store is the derivative of an add operation, such that when we go back, we could figure out what calculation we have to do to get the derivative. And guess what? The derivative of an add operation is it's not really anything. You just pull the it's the same as what the output is. But a multiplication operation, a multiplication takes two arguments. The derivative is the value of the other thing. So we could store that in these little in these functions here. And this multiplication, if you don't know this sort of this interesting Python syntax, if you define this double underscore mul, that is that tells Python this is the equivalent of doing value star another value. So you don't actually have to type out mul, you can just say star, and it redefines that little symbol for you. What else should we cover here? Yes, okay. So as I said earlier, or when we go back here, when we go do this C backward, you're going to see this all the time inside of neural networks. Let's go look at a real neural network. Where do I want to go? I'm going to go to tiny. Yeah, I'm going to go here. This is what our neural network that classifies digits is going to look like, or well, it does look like. We're not going to rewrite it. We're just going to sort of parse through it a little bit here. When we're talking, when you're training a neural network, actually, this is going to happen in a slightly different. We can look at a different version here. Let's look at just train. All right, this is the value this is the thing we want. You're going to see this in every single every tutorial that tells you how to train a neural network, all the source code that tells you how to train a neural network. This little line right here that says loss.backward is going to be there. And what that is really doing is doing this backpropagation that is defined right here, which is going to take the children of that object. So we have some sort of value, we have this output value, we have C. It's going to take all the values that created that and figure out what the derivative of with respect to each one of those. It doesn't matter what calculation we can create. This is not a neural network specific concept. It turns out this is just all you need to create neural networks, is this kind of idea. The rest of this is very easy. So let's look at what it takes to the lines required to define a neural network. Once you have that, is basically just a bunch of really just a bunch of boilerplate. We don't even have to really. It's pretty much just here and up. So it's 50 lines of stuff to define what a neuron is, what a layer is, and then what a bunch of layers is, what a bunch of layers are, and any sort of calculation that you define. You can define any sort of calculation that you want. You could take the derivative with respect to any part of it. And that's what this is included in one of those. This is a function in and of itself. So, that's I think it's clear that that's really all you need to kind of start beginning to define these. So if we go look at what a real where should we go from here? Does anybody have any questions? Cool. I guess I can talk about let's run this. So let me show you what we're going to be, because I think this will display some useful stuff at the end. I also want to emphasize like the like just how, oh, what happened? Oh, I moved some stuff around, didn't I? That's annoying. Data, where did we define that? Ah, right here. We don't even need this, do we? I don't think so. But anyway, this path is supposed to be data such as Mnist. Yeah.
Question from Andres. Are you using TQDM?
TQDM. That is in this library, or that's referenced in this library somewhere, but I'm not explicitly using it. No.
For the progress
Oh, yes. Yeah. So it does that. It does that neat little thing where it like, well, if it like erases what the terminal would be displaying every time it outputs something, so it doesn't like stack up. The progress bar doesn't stack up, just stays at the bottom like that. Looks real cute. But this is, let's look at a depiction of what sort of value, what sort of things we might be passing into this network. These are our computerized handwritten digits. So all this is like a what is it, 28 by 28 image where somebody scanned of somebody where somebody wrote a little digit down, and we can represent that as numbers. So if we actually like look at what that well, we could look at what that value is. This is like a little characterized animated description of what it looks like. Really, these are values between 0 and 255. I think, yeah. Oh, it was not just reading. Yeah.
What does it mean? Like, what is the most difficult part when you can?
Probably when you just run into like, I can show you an example of what might occur. Well, I think that this particular file actually has a little bit of a problem in it. So I'll show you what sort of problems you're going to run into if I get rid of this here. We want to. Basically, what happens is like sometimes your loss value, which you're trying to decrease, starts going up exponentially, and you can't figure out why. And when it is, you can't really, you cannot take the derivative with respect to any of your values. So you end up just like this network like totally diverging and nothing happening, and then eventually it crashes because you get like your values get so big or they get so small that they no longer fit in the computer memory, and you just get nans. That's a very frustrating. That can be something that definitely happens a lot. Other things that you're going to want to look out for when training neural networks is there's this concept of overfitting. So when you train a neural network, you're probably going to train it on the same pieces of data more than once. It's going to see the same pieces of data over and over and over again. But if you keep doing that, what you're going to get is like, imagine we have like all of these like little values, like kind of like this. Let's see. Yeah, and some of them are out here, and some of them are kind of like that. What we really want is kind of a function that goes like this. Like as humans, that's what we want. But if you were to train over and over and over again on these single values, your function would eventually kind of figure out that like the best way to like optimize for the results that you want, it's gonna trick you. It's like a genie. It's gonna just like click right into these values, which is not actually functioning because that's not the function that you're looking for. Because what's going to happen is you're going to try to use this in production or something like that. And it's going to get a value that it's never seen before that's on this line or near this line, and you're going to be way off. So you need to be careful about like not training too much. There is a Goldilocks zone where you're utilizing your data effectively and you're not overutilizing it to the point where you're actually just making your network worse. That's like one of the very first things that you're going to run into when you're training neural networks. Additionally, I think a big problem is probably like data set diversity. So you need to make sure that you have a wide range of cases. Otherwise, like if you actually were imagining your function like going something like this, and you don't have any values that are kind of in this zone, you're never going to learn what that looks like. So an example of that is if this function, this two-dimensional function, if we imagine a function instead that's capable of driving a car, we need to find a whack ton of edge case scenarios if we're going to learn the necessary abstractions to deal with these types of situations. Now, what's really cool about neural networks is that we don't actually have to like see what's going on over here. Because imagine if there's some type of pattern to what the function looks like. You know, let's think about like what a sine wave looks like. You don't actually have to like, all the network really needs to see is like this window here to kind of get the idea of what's going on. It's like, oh, that sort of repeats. That is just a type of abstraction so that it can extrapolate that out later. So we don't actually have to see every single instance of a particular moment, such as like, if you're going to train something that knows how to play chess, you don't have to see every chessboard ever. You learn particular abstractions that are, again, very difficult to describe as like in English, but that even humans know, because humans are pretty good chess players. They're pretty good drivers. They're really, really good drivers.
How do you ensure that we have provided enough edge cases?
Well, you're going to be so you're probably, when you get a data set, you're gonna get a data set. You know, this little example here does this as well. So this value that I'm this like 6 right here, the network has never seen that particular 6 before. It's seen similar 6s, but it's never seen that one before because we have split the data set into 2 distinct parts. One is just for training and one is just for validation. We never touch the validation set because the validation set is like our sanity check that we're not overfitting. We need to make sure that it's never seen that before so that we can like sort of verify that when we put it out into the wild, it's going to deal with values that it's never seen before. You know, like in the case of I'll finish. Like in the case of like driving a car, it's like, you know, you need to figure out that the abstraction might be like a kid bouncing a ball, not a kid bouncing a red ball or something like that. So you might put the green ball in your validation set to make sure that it can still it still sees those as the same thing. Yes.
2 questions. One for me is, so once you train the AI with a training set and you like set it out in the world, it's the wild of the validation set, does anything you put in, like the AI sees in the wild, become like something it knows? Like it kind of becomes part of the testing?
Yeah, I don't want the validation set you would use like in development to make sure that our network is on the right track. So we do a bunch of training and then we're like, okay, our training data, like when we do this right here, so we get this little like accuracy rating, or we get this like loss value. This loss is getting pretty low, but this loss only represents the data that we're training on. So it's seeing the same values over and over again. What we actually want to check, like to see that it's, you know, that could be lying to us. So we need to like really test it with the values that it hasn't seen. That's how we actually calculate accuracy. But when you're out, I'll get to your, out in the wild, all like sort of advanced artificial intelligence projects, like these self-driving algorithms, are trying to collect as many edge cases as they can from out in the wild. So basically the biggest challenge in artificial intelligence, at least in some people's opinions, is figuring out what your loss function is such that you can take advantage of like all of these little edge cases, because you can only ever do something, you can only ever make changes to a network if you've done something wrong. So in the case of like open pilot, this capable of driving car, how do you figure out when something went wrong? You need a signal, because 99% of the time that data is just going to be nothing. It's just the car doing exactly what it said. So like, what are we going to do with that? Well, you wait for the driver to take over the car. Like the driver took over the car there. So look at the past like 30 seconds and figure out if something went wrong. Because if the driver took over on the highway, they probably didn't want to. So something went wrong, and we can backprop from those sorts of errors there. We can take that data and run the model in simulation to see what it did, and then construct very, very weird simulations to try to determine based off of the data that we've seen from human drivers, what it ought to have done, and then try to correct it in that direction. Because again, like all we can really do is see what the network did and then see what we hope that it did, figure out what that value is, using that to determine how we ought to change all the value, all the weights in our network. The weights inside of like a self-driving car algorithm are going to be millions. To classify digits, you probably only need a few. You might be able to do it with a few hundred, a few thousand. You know, the example here, I think, uses about 20,000. To drive a car, you're going to need millions. To do natural language, you're going to need billions, hundreds of billions of values. So figuring out how to like finding those little moments such that you can make the most of your computers. We want to find the pieces of data that like what you can actually do is actually sort by loss. Be like, who had the highest loss? We're going to start with that data, because that's the catastrophic scenario here. So like, I don't know what Google does, but I would imagine if they were smart that they would wait for, I'm using Google Assistant, I say something and then my tone changes immediately. And I say, oh, shut up. Like, you clearly, just something to indicate I'm not talking to it, but I said something was wrong. You need to go to that exact moment and figure out what went wrong. Otherwise you're wasting compute in training your network. I don't know. It was sort of a long tangent, but.
The second question comes from Andres. What is the split for validation and training set? 25-75?
Something like that. I don't actually know what the Mnist. I mean, we could probably look at like basically just based on. Let's just look at like the file sizes, see what it says. So they use images. Yeah, so it looks like about like 10 to 1 to 9 or something like that. So there's many more training images, because we only need to validate accuracy. We don't actually need to like really use that data is not important to us, other than making sure that we're on the right track. Because if we're not, we basically need to go back to the drawing board and figure out why we're overfitting or whatever we're doing. Does anybody have any other questions? Be happy to answer any questions. So how do we actually like, say we're going to download PyTorch, okay? We have it on our computer. What do we actually do with that? This is I'm not using PyTorch right now, but I'm using something that basically has the exact same syntax. The exciting part about it is just that we can actually like read the source code. PyTorch is previously, as of very recently, a project by Facebook with probably millions of lines of code. So figuring out what a function actually does is basically impossible. Doing that with this library called tinygrad, which is as powerful as PyTorch, we can go look at exactly what a tensor is, which is really cool, because you can then see like, you get an error. Why did we get an error? It's really not that hard to figure out. It's like, we go down to our like dot product or something like that. It's like, oh, there's that's why that shape error occurred. That's my little side tangent there. But what are we actually going to do? Where was I? I can't see with this stupid bar. First, we're going to define the most simplest way. You don't necessarily have to go about it this way, but this is the most elegant way to go about it. We can just define a class for what our network is. So we're going to call this one TinyBobNet, just like sort of a thing that some people do with very simple neural networks. And then when we initialize it, so this is a function in Python, this _init. That's just like when that function gets called when we do this right here. So when we like call the class, this gets initted. So we're just going to initialize two values, which are two layers. That layer is a layer that goes, we can think about these as matrices, actually. A layer and a matrix are, in the eyes of the computer, basically the same exact thing. And we're going to go from 784 neurons, which are inputs, because again, our like image classification or our handwritten digits are 28 by 28 pixels, 784. And then we're going to go to a layer in the middle with 128 neurons, which is quite a lot, to just an output of 10. So there's only one hidden layer. Like it's just a whole bunch like that, and then one hidden layer, and then our outputs, which are like, you know, something between 0 and 9. And then all we have to do is define like what happens when we pass a piece of data into it. So our piece of data is actually going to be this like just vector representation. It's a one-dimensional vector representation of that handwritten digit. And what happens when we pass that in? Well, as I mentioned earlier, we're going to do these dot products, or we're going to do these. You have a question? Well, I guess all vectors are one-dimensional in a way. It's a vector. So we're going to like I guess that's something that we could talk about, is that the one thing with these layers is that these layers are not two-dimensional. So if we have a two-dimensional image, we have to turn that into a one-dimensional string of numbers. So we might take the first row of 28 pixels in the second row and put it right here, and so on. So that's why that gets turned into a vector that is that long. But that's sort of one property of these neural networks, is that because there's only like this vector of neurons, like a list of neurons that is not two-dimensional. So if it was two-dimensional, you might have like a square of neurons or something that all have these like tons of weights coming into them. But in the case of these, it's just a list. So we have to convert everything to some type of list. Luckily, dot products are pretty easily defined for one-dimensional vectors. By the way, if you ever see dot, that is the same thing as a matrix multiplication in the eyes of everybody in neural networks. I feel like when you learn that in school, that's not the way that they would say it, but that's the way that they say it there. So if we were to pass a valid two valid matrices to this dot, which again is, if you remember how matrices work, like the size matters. So you have a M by N matrix, you need to multiply it with an N by like P1. These two values have to be the same. But if you were to pass a valid looking matrix to that, it would do that multiplication just like it would do a dot product. And if you think about what a matrix multiply looks like, it's actually just a lot of dot products too. It's all dot products, bro. It's all dot products at the end of the day. So what you actually need to define is how that information is propagated forward. And the way that we do that is that we take the dot product of the input, which is X, with our weight matrix between the input and the next layer, which is layer 1. So what that actually looks like is we have like, that is like a valid, what we have is a 1 by 784 matrix, otherwise known as a vector, like a times a weight matrix that's 784 to, what is it, 128? So the output's going to be 1 by 128, which is the number of neurons in that layer, which is the number of neurons in that middle layer. So that's how we like figure out what the activations on that middle layer are going to look like. You kind of get what I'm saying? Like when we get, if we want to figure out put this matrix in here. So this matrix is going to actually represent, we have, I've drawn 3 weights here. Sorry if it's hard to see. Let me. This is why linear algebra came up earlier. So I hope that isn't terribly visible. But this will make the linear algebra correlation will make sense and why we can sort of use the scalability of linear algebra to our advantage when doing neural networks. So if we represent like how many weights are going to be between these 2 layers? This one's 5, this one's 3, and we need a connection between every single one. Well, every single one that's like sequential. It's going to be 5 times 3, which is 15. And it's actually going to be like a 5, well, it might be 5 times 3 matrix right there.
So how would we even determine what's the number of neurons going to be in the next layer?
Well, we've already like defined that, like this, we've defined it right here by saying that like, when you read this, you would read this as like the input has 780. The first layer has 784 neurons, and then the second layer has 128. And then because we need some sort of like way to get from one to the next, we need 128 in the next one. But those 2 are actually like the same layer, if you kind of get what I'm saying. And then the output is 10, because like what this really is in reference to is like the dimensionality of this multiplication here. So if we multiply, the output of this is going to be a 1 by 128 matrix, which we would then use in a 1 by, I think we might do a transpose or something like that. Let's see, the output is going to be, it's like 10, 128. So you actually end up doing like, yeah. We take that, we have this little output here, which is going to be this. Like this becomes this. We multiply it with the weight matrix between that hidden layer and the output, and we're going to get a 1 by 10 matrix output.
So is there any reason why we want to have like layers?
I think, yeah, well, we totally can get into this. So the history of neural networks goes back, like, depending on how you look at it, over 100 years, probably about more realistically about 80 years. And it wasn't, so that was in like the 1940s that the first like form of what looks really similar to a neural network was discovered. But this was a thing that only had 2 layers. So this was the entire thing. If you imagine, I can actually pull up what I'm talking about, because it actually is quite visual. If we call up Perceptron original, or what is it called? Huh?
What original?
What was the original? I'm like totally blanking. Yeah, Perceptron Mark 1. So what this actually, this was built in the 1940s as a way to basically do that, like that Mnist image classification, Mnist Data Set. Do something like very similar to this, but it didn't really work. So it has a bunch of like photoreceptors on it. And there's like an identical connection, sort of like if you imagine these as like little photoreceptors to a bunch of outputs, and you do a very similar calculation. But it didn't really work because apparently it turns out that this relationship is only ever linear. And linear functions cannot approximate that many things. So imagine we have like a data set where like these values represent like some type of class. Say this is like dogs. And then you have to imagine them as being like coordinates almost. And these are like cats. So you can find a distinction between those that is linear, which is this line right here. But if you imagine that like the data set was more like these were the things that we were after, you need a more complicated function to like get around that. Now you can't actually do that, but you had to go like that. So that has to be a nonlinear function. And it turns out that the only way that you can get a nonlinear function is with hidden layers like that. So you need to have at least one hidden layer, which is this part right here, to get a nonlinear classification system, which is pretty much every single thing that we want to do. There's not really many linear classifications that we might want to find because they're pretty easy to do like otherwise. Does that sort of? Yes. So this is like what I'm describing right now. This is like a hardware instantiation of that. So imagine if we like literally wired up this this mechanism that we're trying to make. And it actually did kind of work. It could recognize like blobs, and it could see sort of like you know, it was sort of like you had a type of, you had like you know, like a blindness where you could like see patterns of light and shapes and things like that, but you don't have a very detailed vision. And like part of the reason is that you could not do like this could not approximate a complex function. This could only approximate a linear function. So if we think of our things in terms of functions, there's not that many things that are very interesting that are only linear functions. Most of them are highly nonlinear. They're very, very complex. They're wild. They're like unpredictable. But that's because like dealing with the real world is quite unpredictable.
Question is, are you familiar with
What? How is it pronounced? Or what is it? Jeffrey Hinton? No, I'm not sure. But yeah, I'll have to.
I have a question. So, how would you determine what's the like initial amount of like nodes like neurons is going to be when you first started that like movement to the layers?
You're probably just going to like define it on your own. So like when I made this one right here, I just kind of was like, well, first of all, I knew what my input size was going to be. You have to know what the input size and the output size is, because like otherwise, what are you making your function for? So if you're going to make a function that tells you how to like recently I was reading something about a neural network that was like learning to control the motors inside of the legs of a quadruped robot, otherwise known as like a robot dog, like one of those Boston Dynamics things, where the neural network has complete control over like the angle of the servos in the leg. So the output of that, there's 3 motors in each leg, there's 4 legs. So you already know you need 12 outputs. And then you have to come up with some sort of number to describe your inputs. How many inputs do you want? Like how many inputs do you have? Like you have like accelerometers, you have, you know, you might have a camera feed, which is going to be like massive. If you want to combine all of those things into one giant input, you know, maybe you can try. So you're going to figure out what your input and your output is. You know that those are going to be some sort of value based on what you're using it for. But what happens inside of that is really up to you. It can be whatever you want, and you're going to want to do experimentation. So if I wanted to add a layer, like we add 1.5, well, sorry, let me do that. Imagine that's a 0.5. I could do one that's, I'm pretty sure I could do this. right? Maybe I train my network with that instead. I do a little modification to it, and I find out that having that middle layer improves my network's ability to find patterns a lot. So neural networks are this small like toy tiny Bob has two layers. The ones that you're going to make to do like real things are probably going to have maybe upwards of a dozen, maybe like 5, maybe 20. And you're going to have to experiment with what like the number of neurons that works best for your circumstance. That's also why I sort of think that you have to come up with a way to learn those, what optimal patterns of neurons looks like, but that's a complicated, that's a difficult problem. But do you kind of see what I'm saying? Where ultimately, at the end of the day, it's a function. So your function, there's 2 critical things that you have for your function, which are what your input is and what your output is. What happens inside, I don't really care.
So it's just a case of finding inputs and experiments.
Yeah, like you need to strictly define. You're like, what are the parameters of my project? The parameters of my project are like, well, I have this like 1920 by 1080 camera feed. I can already tell you that's going to be way too big to pass into a neural network. So you're going to have to do some sort of pre-processing on it to reduce the resolution and maybe pull a couple of abstract, like pull a couple of patterns outside of it to reduce the size of the data. Maybe that's one of your pieces of data that you're going to pass in. You're like, well, what else do I have? You know, I already mentioned your like acceleration and stuff like that, but.
When you say way too big, why would that?
Well, let's the computational, like I don't know what the like O of the computational like complexity is for neural networks. I don't, but like it's massive. So you need to your compute for doing these types of things is although like tuning a thing to classify digits was quite fast. For any sort of complicated project, you're probably going to not be able to get your hands on enough compute. You'll take anything that you can get. And that's the situation that all of these artificial intelligence companies are in right now, which is also partially like why like the graphics card aftermarket is bloated, because like if I'm an AI company, like a 3090 to me is worth so much more than like it is to a lot of consumers, simply because of the number of calculations that it can do. And I'm going to do is I want to make my network as big as I can. There's data that basically like, I'm not going to say proves, but strongly suggests that like bigger networks are capable of more things. There's a pretty linear correlation between how good like a natural language processing network is, so something that's good at English, and how many values it has. So earlier we were talking about, funny enough, it heard me. You know, the number of values right here in this matrix is 15. You know, Google Assistant probably has, I don't know, maybe 100 billion. Because imagine like what happens if we make this input like 1,000. 1,024, and then the next one 1,024. What's 1,024 squared? Big number. And then you do that for like 20 more layers. Training that, finding those derivatives becomes a massive task. So you want to be, they're always looking for ways to make that computational intensity less. You may run into things called transformers. That's a very popular thing in machine learning right now. They're very popular for natural language processing. This is basically like a computational trick to make something called recurrent neural networks actually practical. Tricks to reduce the amount of data that we have to deal with and the number of parameters that we have to deal with are like in high demand, basically.
Okay, so like when you talk about like computational power, some of the aspects required by neural networks take a ton of computational power. Computers and stuff, like you're gonna do like a basic personal project, like a personal neural network, just like as a personal project. Would like a normal, like just like a normal laptop, would you handle that before? Like,
I think so. Yeah, like the CPU in your laptop is very, very powerful and capable of doing a lot. If you're, I know a lot of people are like gamers. Graphics cards are exceptionally good at processing what are called tensors, which is like what this thing is. A tensor is like looks like. Imagine this, but like you could go even, well, you see we have like a 1D tensor, 2D tensor, 3D, which is like a cube. You could just go arbitrarily deep. And you can do multiplications, you can do adds between these types of objects.
The vector, this is like two-dimensional vector that is subset of a tensor.
Tensors are a more abstract class of like what a matrix and what a vector is. It's a, you know, you could, I think it would be edgy to say you have a 1D tensor if you're in like linear algebra or something like that. But like, or like a 0 rank tensor is like a scalar. It's just a number. It's like, but ultimately, yeah, those are like isomorphic concepts. But yeah, anyway, like also like renting compute to train neural networks is very affordable actually. You know, there's hardware that costs $10,000 you can rent for like $2 an hour, and your training is probably going to take like, I don't know, 4 hours or something like that. It's often quite reasonable if you're doing like just a side project to like Google like you know, like rent A100, which is like very similar to like a 3090 or something like that, just has like more memory and like more memory bandwidth. So you can fit like the biggest hiccup is not really actually compute right now. It's actually like how big of a network can I fit in the memory of my graphics card? Because you can't be moving information to and from like the CPU memory to the GPU memory. If you are, you're gonna be like 10 times slower than you would have been otherwise. So like A100s don't have like that many more floating point operations, like multiplications per second, but they have more memory. So they end up costing like 5 times as much as a 3090. But you know, renting those are very affordable. Yes.
The question is for cloud training, would Lambda Labs be used?
I've seen ads for Lambda. I've heard positive things about Lambda before.
Lambda Labs is actually pretty decent. I used it once or twice. It's cheaper than Google Cloud, cheaper than Google Compute. I am not sure of its security.
Yeah, the biggest hiccup with cloud training is probably getting your data to and from somebody else's server. So the really convenient part about if you have like a gaming computer, doing it locally is like all the data is right there, and I don't have to, because imagine how big your training data might be. If your training data is video footage, it could be many gigabytes or images. Getting that to and from somebody else's server can take a long time and might also cost you more money. This is why like typically large AI operations have their own servers, because it's just not practical to rely on somebody else's servers if you're training 24/7. Additionally, like some of them have, such as Google, have restrictions on what you can use their hardware for. Google has incredible hardware for processing tensors, much better than much more interesting, much better than anything that you can buy off the shelf, and they keep it all to themselves. You can rent it if there's availability, but you can't use it for anything that competes with Google, which is a lot of things. They will ban you, maybe sue you. So no self-driving companies are going to be using Google Cloud's TPUs, because that's competing with Google Waymo. You're not going to train like a competing voice assistant or like any sort of text processing. So it's got its uses, but it can be very aggravating to like, you want to use it and there's no availability, so you just have to wait for the availability to come up. It might be like hours or days or something like that. Anyway, yeah.
So like, if you have like just a regular, like, it's like one of those regular like office laptops, would it be wise to like invest in like a high-end gaming laptop with an RTX card to like compare it?
If you're doing neural network things if you're developing neural networks on your laptop often, yes. But if you're not running into problems, like if I try to load a neural network that doesn't fit in the memory of like the GPU that's on my laptop, which is not, this is not an example. But if I had a laptop without a GPU or with a GPU or something, it was so slow that it was unusable. Or if it did have a GPU and like I couldn't process what I wanted to process, you would know if you had a problem. If you have a problem, then yes, I would generally say until you have the problem, wait. But I guess I will. Oops.
Like, what would be the best resource that, in your opinion, like, what's the best resource, like YouTube channel or whatever, like, the best place to like learn about like machine learning?
I think probably the best is like blog posts from companies that seem to be doing interesting things, or like papers from companies or think tanks that are doing interesting things. So DeepMind and OpenAI are perfect examples of these, and they publish a lot of papers. They have like people will post commentaries. There's a really great YouTube channel called like 2-Minute Papers that posts. I'm not going to pull it up, but it will do like reviews of. We'll go over like the advanced topics inside of a computer science paper for sort of the like computer science layman. I think that's a great channel. I think there's a lot of really great repositories on GitHub that sort of teach that that are within reason to read and understand what's going on. So this one is probably a little bit is almost certainly too advanced, but the one that I've been referencing earlier. No, I don't actually want to go here. I want to go. Is this repository right here. If you're really interested in neural networks, I would highly recommend just like looking through the code of this repository, because this will tell you exactly basically how one works. That's what we were looking at. Open it. That's what we were looking at here. So this defines like using things that can do derivatives, things that have autograd. You can pretty easily define what a neuron is, which a neuron is like the list of weights that are coming into it. So this one has these weights. And then there's actually a bias. That's not something that I was going to cover today, but that's defined there as well. And then this activation function you don't need to pay attention to. And then guess what? Like a layer is just a list of neurons. And we define how many we want just based on like how many values are coming into that layer and how many are coming out. And then a whole network, a multi-layer perceptron. If we think of this, this little thing this layer is like a perceptron, the single neuron is a perceptron, a multi-layer perceptron. All we need to do to define it is like define how many we want in, and then this n outs is actually a list. So if we this is a description of a network right here. So we define our multi-layer perceptron is just a thing with these inputs, and then this is what the hidden layers look like: 16, and 16 neurons, and then 10 on the out. And then every time we like, all this little optimizer thing here does is every time that we like figure out what our gradients are, all we need to do is like step the value of that weight down, which is this data value. The parameter we could think of as the same as a weight. So the value of that weight, we're just going to step down by some multiplier of its effect on the output. If that effect were negative, then we would be stepping it up. But that's, because that's just how this like this subtraction would work. And this learning rate, which is the thing I covered earlier, is if we were to step it down by the entire gradient, we would go too far, almost certainly. And we're trying to, what we're really trying to do is like, say we have this function right here. We're really trying to find a minimum. Sorry if it's, I'm gonna get rid of this. What we're really trying to do when we're taking these gradients, so we get this, like, we find a value right here, and we find the gradient is like this. We find it's really dramatic. We're trying to find the point where the function is minimized right here. So I'm going to step the value down. Say I end up right here. We're a little bit less. So I know I'm probably a little bit closer to what the minimum is, because the slope is like slowly decreasing, and then I step it like a little bit less, and then a little bit less here. But imagine if I had stepped it by like not by the entire gradient, or by some even bigger number. I might end up over here, and now I've overshot it, and I'm like confused. I'm like, okay, that didn't really, my step didn't improve the performance of the network, so I must be in totally the wrong area. Let's move around. Even though I was in the right area, I just didn't know which way to go. So that's why you had to do that. Additionally, like neural networks will often, this one does not do that. We could code it to do that pretty easily. Will decrease the learning rate over the life of the network. So you want to start it big because your network's totally wrong. All the values are random. As I make a little bit of progress, it's totally random, they're totally wrong, so I want to make big progress in the beginning. But then I get a little bit closer and I want to make less, and I want to take smaller steps because I know I'm probably pretty close. So I'm going to slowly decrease the learning rate over time. And the learning rate is just this LR value, this multiplier of how much we're going to step the value of the weight. I hope that kind of makes sense. Let's see what else we could. There's 5 messages here. What's up? Should I read it? Or should you read it? Here's a list of good papers. I would probably agree with that. Okay, maybe open that. What about getting stuck at a local minimum? How do you avoid getting stuck at local minimums? So sometimes you're probably going, gets to be sort of an advanced concept, but you're probably going to, like, every iteration pick a handful of weights to just like randomize or zero out or something like that, because they might very well be in the wrong spot. You might be at like this local, you might think you're at the minimum here, but really there's a better minimum way over here. So by random chance, this unlucky weight, we're gonna just like change to be way over here or something like that, and hope that that's like not a worse value. We also might, yeah, I think it's. We're not doing that in any of this training right here, or any of the things that I've like covered, but there are problems where like you get this like stagnation in the way that in like your network where it's not improving properly. So you might want to like jiggle up the weights essentially. Is it by making your step? How do you avoid getting stuck at local minimums? That's basically why you probably want to, that's why you need to start with a learning rate that's pretty large and then slowly step it down over time, so that you hopefully end up in like the basin that is the biggest minimum. Luckily for that, the biggest minimum is probably going to have like I say probably, not necessarily, but like the biggest sort of area or like distance. So like you're not as likely to end up in this area as you are to end up in this area, because like you're it dips so much more, so it probably needs more like space to dip. That's not that interesting. I don't think. Let's see. I don't really think I have that much more else to cover. If anybody has it. What's up, Andrew?
Would you recommend micrograd then, like to create neural networks?
I think using micrograd to learn how neural networks work. One problem is I mentioned just how like efficient tensor calculations were. So I actually wrote the same neural network twice. One in TinyGrad, which is capable of doing tensor operations, and one in micrograd, which only stores values as just these little individual values. So it can't do like massive parallelized blocked operations. It's basically impossible to train to classify digits. If we go like when we, it's so unbelievably slow for that reason. Like that's what I'm talking about. We're talking about like thousands of times slower, but at least I think conceptually it's easier to understand. If you let this run for like a long time, it would basically get as good, but like it's not practical. I mean, we're talking like many, many hours versus a couple seconds using a proper tensor library. Anyway. Yeah, I don't think I have anything else to really cover. TLDR, things that are useful for neural networks are things that you can describe as algorithms or as functions. So if you could think of a way to just, if it's easy to say whether you did it right or wrong with data, and it's a very difficult, if almost impossible function to write, it might be an ideal candidate for a neural network. It's worth looking into. It's probably good if you can describe it just in terms of like regular Python, it's almost certainly going to be 1,000 times faster if you just do that. But many problems are not. Anyway.
Apples or like if you want to get into like what are the examples of them?
I think like a perfect beginner example is probably image classification. Another one might be like you can look into like predicting like the connotation around a sentence. So you can train it to understand if a sentence, if like a review of a movie is positive or negative just based on the content of the words. Another one that is interesting is like if you look into recurrent neural networks, the first thing they'll probably show you is like how to make a thing that can predict, that can talk. So it will, based on like the last 25 letters, predict what the next letter is going to be. I think that like there is some like interesting techniques that you have to take to do that, that will like enlighten you as to what, how to do these little tricks with neural networks. I think at this point, it'd just be people that want to hang out and talk about neural networks. Resources on campus, not that I'm aware of. There are classes that have a lot of prereqs, but I cannot co-sign their quality or not.
I mean, if you are an ECE major, there is a new class on campus called machine learning, taught by Dr. Ed. It's a 4th year course. It might be still here in a few years. So,
What's the number?
ECE 40. It's 4,000. It's a 4,000 class.
What's it called? Like, is it just called machine learning?
It's literally just called machine learning. Yeah.
Oh.
Need this.
Oh boy, that's a wall of text there.
So,
All right, I'm gonna head on out. You guys.
see you. Thank you.
Why is Python the preferred
All right.
language
Thank you everyone for coming.
Why is Python the preferred language?
for machine learning? You mentioned that Steve was a factor.
I don't think Python is not,